Hi, welcome back to MEEN 221. Today we are going to talk about how to do a step-by-step calculation of forces in a frame. Now, we have done this many times before. I mean, it's just a free body diagram and calculating all the forces and things like that. But what I'm going to do is much more systematic numbering and labeling scheme so that it's extremely easy to write down. That's item 1. Item 2, I'm going to skip some of the steps because I want you to get used to the fact that you don't have to draw that force table for everything. We are going to do a direct vectorial version because I want you to start being able to do the symbolic version quickly. Okay, so let's start. So we are going to look at an example of a bookshelf. So let's see what the story is. So this is our first example. Here's a bookshelf. You can see that the bookshelf is put up there and most of the books are on one side, and if you look at this thing, it looks something like that, right? That's the structure which we are going to analyze to figure out how much load is there on each of this. Okay, that's what we are trying to find out. So we have to make some approximations. It doesn't come with axis labeled and joints known and things like that. So let's make a rough idea and then we will see what happens. So we are going to look at just this portion. Here is the bookshelf, and let's say that the total width of the bookshelf is 2 feet. That's a fairly large one. You can see it's fairly large, and we have to decide what's the weight of all these books up here. And we are going to do a generous factor of safety so that we want to design this properly. So I'm going to put a weight of 80 pounds in the middle of the bookshelf. There it is, 1 foot from here and 1 foot from here, and let's assume that this angle is 45 degrees. So this is also 2 feet, right? So that's our structure. Now we have to decide how is this bookshelf connected. You know, up to now in your previous problems, these connections were always given. It was said, it was obvious to you by looking at the picture that things are pin joints or welded joints or something like that. Here you have to decide. In our particular case, we are going to say, look, you know, I'm going to kind of not just put a nail into the wall. It's not really a big bolt or something like that. This is stuff that you have to decide. So the typical choice is that we are going to assume that all joints are pin joints unless it will not work. So I'll tell you what I mean by that. In most cases, we will assume that things are pin joints. That's our first assumption. When I connect two things, I'm going to assume it's a pin joint unless you can see that clearly it's welded or something like that. When I'm putting a screw through something, it's not tough enough to hold bending forces, and you don't want to damage the wall with bending forces. So what it is that I'm going to assume this is a pin joint, point A, and then point B is a pin joint, point C is a pin joint, point D is a pin joint. That's item 1. Item 2, always so. Step 1, decide on joints. Step 2, label the rigid bodies with numbers starting with the ground as 0. This is quite important. So many times we forget about the ground. So I always want to make sure that we have. So this is 0. This is rigid body number 1. This is rigid body number 2. Okay. Then step 3. Label the connection points and the locations where forces act. This is important. So we got A, B, this point is going to be called C, and this point is going to be called D. Those are A, C and D are places where things are connected, and B is the place where the weight W equal to 80 pounds acts. Now step 4, draw separate FBDs for each. So I'm going to draw this here. Excuse me. So there's a rigid body 1, this point is A, this point is B, this point is C. That's rigid body number 1. Okay, so far so good. Now what it is that at point A there is a pin joint, and instead of drawing two forces at pin joint, I'm just going to draw a force vector here, A, and I'm going to label it as A1 vector. So now I'm not going to draw A1x, A1y, I'm actually going to just write it up here as A1x, A1y, 0. So I want to make sure that, hey, I want to do the same thing for both 2 dimensions and 3 dimensions. So what this says is there are two unknown forces, A1x and A1y, and it's a pin joint. How about point B? There is W acting downwards, and how does that show? I'm going to call it W1, and it's a vector, and its components are 0, minus 80, 0. And at point C there's another pin joint. So I'm going to draw a line like that, and I'm going to call this C1, and its components are C1x, C1y, 0. You see that? And then I'm going to draw for the other one, which is like this. I'm going to call this point D, that's the force there, and this will be called D2 because it's a second free body diagram. So what it is that this, I'm going to write this out. So this represents rigid body. So tells me which rigid body we are talking about. So now I'm going to have C2. Notice I don't care, I'm always drawing it in the first quadrant. I don't care which way things are going to point. Everything will be there in the vectorial notation. So let us not get too worried about it. So I'm going to write it as C2x, C2y, 0. Right? And the beautiful thing is I can draw coordinate systems, different coordinate systems for different bodies. So this is going to be xy for this, and this is going to be xy for this. So you can use different coordinate systems for different bodies. No problem. Okay. Now notice I have called this C1 and this C2. Newton's third law will be written like a equilibrium equation. It will be called joint equilibrium. And it will tell me that C1 plus C2 equal to 0. This is the same thing as saying C1 equal to minus C2. Can you see that? So what it is that rather than trying to do different things, I'm just going to write everything like equilibrium equations, because then our life will become simpler. As we get more complicated forces, our life will become easier, and this is the way to do it. So this is a very important idea, so please pay attention to this. So rather than call it C1 and minus C1 and getting confused with signs, I'll just call it C1 and C2, and I'll use another equilibrium equation which says that there is no net force on the joint, so C1 plus C2 must be equal to 0. Okay, very good. So this is our starting point. It looks very messy, but you will see that it will get cleaned up pretty nicely. So let's go. So what happens is, here is our free body diagram. Here is our coordinate system, y, x, y, x. Everything was written here, and we knew that C1 equal to minus C2. Now we are going to go directly, instead of drawing force diagrams and force tables and things like that, we are going to go straight out and write the vector version. So summation of forces equal to 0. Vector version looks like A1 plus W1 plus C1 equal to 0. and this gives me two equations, a1x plus 0 plus c1x equal to 0. That's equation number 1. a1y minus w plus c1y equal to 0. That's equation number 2. Okay, so notice that I am always keeping the index. Then summation of moments around A equal to 0. I am going to write this in vectors. So remember, this is the point A, this is point B, this is point C, this is point C again, this is point D. Summation of moments around A equal to 0 will give me, notice how I write it, AB vector cross W1 plus AC vector cross C1 must be equal to 0. Notice some key things. This A is always the first letter. That's the point around which point for moment. B is point of force. So it will be AC cross C1. So now you can use xfy minus yfx to find this. In our case, I'll show you what I mean. There you go. AB has x component 1, 0, 0, AC 2, 0, 0. So you can do xfy minus yfx and all this stuff. You can calculate all of this. I'm not going to waste your time. I'm going to go directly and write down, and I will get, let's see, what will I get? I will get minus 1 times w plus c1y equal to 0. This is my third equation. This will give me this. Okay. So I got 3 equations. That's all you can get per rigid body in 2 dimensions. Only 3 equations per rigid body. In 2D. In 3 dimensions, you will get 6 equations per rigid body. In 2 dimensions, you will get 3 equations per rigid body. What I want you to do now is go get a pen and paper and you do the same sequence for this rigid body. Go ahead, do it. Pause this video, go do it, and then you can compare what you have with me. As I said before, you cannot build muscles by watching an exercise video. Okay, so the best thing to do is pause, take a piece of paper, you try the same sequence, and then you can look at what I have done. Okay, so did you pause? Did you try it? Okay, so what I have is the following. Summation of all the forces equal to 0 gives me D2 plus C2 equal to 0. That gives me D2x plus C2x equal to 0. D2y plus C2y equal to 0. So this is equation 4, equation 5. I will need one more equation. Summation of all the moments around D equal to 0 gives me DC cross C2 equal to 0. So what is DC? It is 2 units up. Remember, 2 units up, 2 units to the side. Can you see that? Up to side 2. So it's pretty easy. It's 2, 2, 0. So you can go do the cross product, or you can do xfy minus yfx, whatever you feel like, and you will get the following: 2c2y minus 2c2x equal to 0. This is equation 6. Then I'm going to list the interface conditions also here, or joint condition. That's this guy. which says C1 plus C2 equal to 0 gives me C1x plus C2x equal to 0, C1y plus C2y equal to 0. So this is equation 7, this is equation 8. So we got 8 equations. I'm going to write all these 8 equations down. You can take a look at it and you can figure out whether you got the same things. But this is the whole deal. After this, it's just algebra. Okay. So let's do this right. So here are the 8 equations. A1x plus C1x equal to 0. Equation 1. A1y minus 80 pounds plus C1y equal to 0. Second equation. Then minus 80 plus C2y equal to 0. This is third equation. Sorry, 2 times that. And this is C1. Excuse me. Okay. Then we have d2x plus c2x equal to 0. That's the fourth equation. d2y plus c2y equal to 0. That's the fifth equation. And then 2c2y minus 2c2x equal to 0. That's the sixth equation. And then c1x plus c2x equal to 0. That's the seventh equation. c1y plus c2y equal to 0. This is the eighth equation. So now you have two options. You have 8 equations. Let's see how many unknowns. a1x, a1y, that's 2. c1x, c1y, that's 4. c2x, c2y, that's 6. d2x, d2y, that's 8. So counting 8 unknowns and 8 equations. You can go one of 2 ways. You can just use a matrix program to do this. That's why we teach you MATLAB and other things. And if your calculator is good enough, you can do this 8 by 8. Or you can be a little bit clever and you can solve it pretty easily. So it's either way is fine with me. So I'm going to show you what's the easy way to solve it. So what it is that I'm going to solve it from here. Okay. Notice 3 will give me C1y equal to 40 pounds. That's really good. Then what happens? If I take that, 2 will give me A1y equal to 40 pounds. Okay, that's very nice. But how do I get C1x? So I am looking around and it turns out that C1x equal to C2x. So 7, 8 and 5, sorry 6, 7 and 8, 6, 7, 8 give. This C1y is minus C2y. So 8 will give you C1y equal to minus C2y. So which implies C2y equal to minus 40 pounds. Which implies from 6 C2x equal to minus 40 pounds. Then from 7 C1x equal to 40 pounds. Right? And then from 1 A1x equal to minus 40 pounds. And then from 4 d2x equal to c2x, which turns out to be d2x equal to minus c2x, which turns out to be 40 pounds. And then you can get d2y equal to minus c2y which turns out to be 40 pounds. Right? We got all of them. Right? So you got to kind of look around and solve all of them. You can see I got all of them. So that's how we solve it. Okay. So please remember that if you do it in a systematic way, it's possible for you to solve everything. Thank you very much.